Welcome to C&EN Uncovered. I'm Craig Bedenhausen. C&EN Uncovered is something new we're trying on stereochemistry. In each episode, we'll take a deeper look at a recent cover story in chemical and engineering news. C&EN's savvy chemistry reporters will share striking moments from their reporting, their biggest takeaways, and what got left on the cutting room floor. In this episode, we're diving into a cover story from last September about exascale computing and what it could mean for chemistry. I'm here with Ari Remmel, who wrote that article. Hi, Ari.
Hey, Craig. Thanks for having me on the podcast.
We'll link to that article in the episode's show notes, or you can find it in the September 5th print issue of C&EN. That's September 5th, 2022. Definitely check it out if you haven't already. But I think a good place to start, Ari, is for you to explain what exascale computing even is. It's kind of a big, scary word, and it was actually new to me, too, before I read the article.
Yeah, so my role with C&EN is to make sure that our audience is up to date with developments in physical chemistry, computational chemistry, astrochemistry. And exascale computers, which is a new generation of supercomputers, actually falls really nicely into the kinds of stories that I already write about. So chemists have been using supercomputers for about as long as supercomputers have been available to us. These systems are able to do a tremendous number of calculations, which their computational power is measured in a unit called floating point operations per second. And floating point operations are basically a fancy computational arithmetic that can handle like scientific notation, numbers where the decimal places kind of move around. So a standard kind of laptop computer is going to be able to do something on the order of billions of calculations per second, which is why our laptops can handle all of those tabs, so many tabs. And it's also why they can help to render really lovely, clear displays, images, and help us visualize molecules. But if we're really trying to study and simulate a complex molecular system in a computer, you need much, much more computational power. So the kinds of computers that fall in this supercomputer realm for chemists traditionally have been able to do trillions of calculations, can achieve trillions of flops, which again is this floating point operations per second. It's definitely a fun word. So in the US right now, the most powerful supercomputer is actually in the petaflops range. It can do more than a quadrillion calculations per second. And in the case of Summit, which is a petaflops computer at Oak Ridge National Laboratory, this computer can do 200 quadrillion floating point operations per second. And this is just like an astonishing amount of power, to the extent that this supercomputer is the one that was used to perform a lot of the calculations that went into kind of the now iconic model of the SARS-CoV-2 viral envelope that I assume that I would bet that our audience has seen kind of all over the internet and various news publications at this point. So all of this is to kind of set up the fact that exascale computers, and in the US, the first new exascale computer is now called Frontier, also at Oak Ridge National Lab in Eastern Tennessee. This computer is going to be 4 or 5 times more powerful than Summit. And that's because it has broken the exaflops barrier. It can do a quintillion calculations per second. That's 10 to the 18. Just absolutely astonishing.
This question may be inside baseball, but these are some crazy words that I only sort of... How long did it take you to wrap your head around these quintillions and exaflops and this?
Yeah, no, that's totally fair. I would say that a lot of what kept me up at night with this story, fact-checking wise, was trying to make sure that I had the right number of zeros associated with all of these numbers. Now, I think that a lot of these kinds of jargon terms, for most chemists, maybe don't matter as much in our everyday kinds of calculations. However, having an understanding of the kind of astonishing level of innovation behind the hardware and its capabilities, I think is really important for chemists to understand, what kinds of doors are going to open in the chemical sciences as we start to apply this new type of instrument, exascale supercomputers, to delving into some of the complexities of chemical systems that were not available to us or within our view with previous earlier models.
Yes, let's talk about that a little bit, because you mentioned that there's the proteins and lipids and things like that of the COVID-19 particle. And you can imagine how you would need a lot of computational power to model all the bending and twisting and squishinesses of a protein. But who else in the chemistry world needs something like this outside of protein lipid people?
Yeah, so anytime that you are trying to understand how materials, how compounds within a chemical system are moving around, these molecular dynamics models, which is what was partially used for modeling the SARS-CoV-2 variant, those are going to be really important.
So it sounds like one of the things you're saying is that in addition to being able to model more complex systems, one of the things this is going to do is let us model systems we might already be able to model, but model a much longer sort of event.
Yes, and that longer time frame has a lot of scientists very, very excited, especially in, the biochemical space, because if we really want to be able to create controlled computational models of biological systems to really ask questions about, what is happening in our experimental designs, which experimental results are still incredibly important when doing computational studies because you've got a benchmark to something, right? You need to know that you're actually studying something that is real. And if it's not, then you can make refinements. But in real life, in living systems, those reactions happen across these longer timescales that have just been out of reach because of limited computational power.
So aside from chemists, who else is competing for time on this machine? Surely we don't get exclusive access.
No, we definitely don't. So Frontier, which I mentioned is the first exascale computer to debut in the US, is the first of 3 that are expected to really go live, be accessible to the public sometime in calendar year 2023. So the other 2 systems, Aurora at Argonne National Laboratories in Illinois and El Capitan at Lawrence Livermore National Laboratories in California, these 2 systems are also going to be online soon. You'll notice that all 3 of these labs are Department of Energy national laboratories. And there's a huge interest in having this computational power to look for more energy efficient catalysts, certainly in the realm of chemistry, but also being able to study turbulence, to study expansion of the universe, these other big questions in physics and energy systems that require just as much computational power. So I know that there are a number of folks in the field of cosmology who are really excited to use these exascale computers to try to see if we can create models of the beginning of the universe and try to really get down to some of the nitty-gritty details of how the universe is expanding.
You went there. You've been to this facility. What was it like to be in this otherworldly sort of a place?
So I drove from Little Rock, Arkansas to Oak Ridge, Tennessee, which is just a little bit north of Knoxville on kind of the eastern edge of the state. And this is like beautiful mountainous landscapes with these lush green trees. It's not technically part of the Appalachian Mountains, but it's not terribly far from Great Smoky Mountains National Park. And so the landscape is absolutely gorgeous. And in order to actually get to Oak Ridge, first of all, you have to have security clearance in order to get past the gate. So, I showed up, gave them my ID. But then the road is the advice I had was just keep going. You'll know when you get there, and it was just absolutely beautiful being in this kind of mountainous valley. But Oak Ridge, the actual campus, is really beautiful. And it looks a lot like a standard kind of research campus. But one of the sources that I spoke to, Bronson Messer, who's the director of science for the Oak Ridge Leadership Computing Facility, he says, yeah, if you look at these buildings, a lot of them were built in like the 1940s when the lab was originally established. But the computing facility kind of looks like it's been like steampunk retrofitted because there's all of these like sort of bits of, duct and retrofitting that they've done to it to make sure that they can fit all of these computers, power them, store them, which is actually kind of wild. So walking in, there's this really cool viewing platform where folks can actually look down into, it's like glass windows you look down into this big white room, and what's directly in front of you is the first bay of cabinets for Frontier. And it's got Frontier written in nice big letters, so you know exactly what you're looking at. And there are engineers moving in and out of these cabinets, or moving around these cabinets. There's 74 of them, and each of them weighs about 8,000 pounds, partially because of just the sheer number of components that's in there, but also, because it's pumping 6,000 gallons of this cooling water a minute. So they're very, very heavy. And one of the things they had to do was like reinforce the floors in order to actually make sure that the floor could hold all of that computing power. When I went to visit the facility in July, the engineers and the facilities managers were still trying to, quote unquote, shake out the nodes, right? They needed to be able, it's really, really funny to think about the fact that like there are just so many components in this machine that things could go wrong, right? And so they have to be able to make sure that each of these components is functioning properly. But the thing that was actually really astonishing to me is, when components fail, they tend to fail at the beginning of their lifetime in a machine. So that's one of the reasons they needed to make sure that they were doing so much work to check all of the different hardware bits at the beginning. When I was there, there was an engineer there at like a little bench with a screwdriver, like pulling these components again that are just innovative all on their own, taking them out, putting them back in. And he had a little CVS bottle of isopropanol there to help with the cleaning. And it was just kind of like astonishing, right? Remembering and having being in a room where there's a clear connection between the people who have built and designed this machine and what is going to be like the incredible science that comes out of it. And I think that one of the points that I talked with folks at Oak Ridge about was, at the beginning, I was struggling with, okay, do I call Frontier a machine or an instrument? And certainly by the standards of, like, computers are machines, it's definitely a machine. But most of the researchers that I spoke to are really interested in how users of these supercomputers are going to use them, right? And so from that standpoint, thinking of this more as an instrument that is a tool for scientists rather than something that's just going to be able to vomit out, self-generate scientific breakthroughs. It's really the people that are going to bring this new age of supercomputing to bear.
Yeah. Yeah, this shaking out the nodes reminds me of when I toured, there's a science history museum at Harvard, and they have one of the early, it was a supercomputer for them. It's like less powerful than your pocket calculator now. But it described, hunting for bugs, which at that time was literally going into the machine and literal actual insects would be stuck in there.
Yeah, it's absolutely wild. And I don't think there are any bugs in Frontier. It was like a wildly clean space, sort of like a sci-fi level, white room, black monoliths of this computer with only a faint buzzing. It was actually fairly quiet in there, which I thought was kind of remarkable. I don't know that there were any bugs. I did try to figure out how many screws there are, but I wasn't able to get a good answer out of that. And, this Frontier and the other DOE exascale computers that are scheduled to come online are all part of a larger project called the Exascale Computing Project, which was established barely more than 5 years ago, right? And so the fact that Frontier was able to get installed during COVID, that it's kept on schedule, and that it's really exceeding expectations in so many different regards, given how short a time frame from proposal to actual execution is really also pretty remarkable.
So what are you looking at next in the field of these big computers?
Yeah, I think that there are a lot of really interesting questions that I'm looking forward to following. Some of just the basics of how we can use artificial intelligence and machine learning to streamline some of the computational tasks that chemists are interested in doing. And I know that was a lot of jargon right there. But in order to teach a computer even the basics of a chemical intuition that we develop over the course of Gen Chem and all of those basic chemistry courses, plus our time in lab, in order for these computers to learn that, they need these massive data sets to be able to start to make the connections, which is how machine learning works, right? If you think about a system like DALL-E 2 or even Crayon, these kinds of AI image generating tools that have gone viral on social media, like those technologies are often developed with millions of labeled images, right? All of these different parameters. And we're just not really at the point now where, number one, we even have data sets of chemical systems that have enough of the parameters kind of worked in. But we've also not had the ability to process all of that data in a way that a machine learning algorithm could really try to start establishing the connections so that it could, quote unquote, think for itself on a never before seen system to itself. So having the ability to train these algorithms with larger data sets that can come from experimentation, which, exascale computing is going to push the need for, but also being able to train them on the exascale computers because they can allow the machine learning to have all of the different nodes that it needs to make those connections, is going to give us access to algorithms that will likely have utility in other areas of chemistry, right? So this is, I think, one of the places where I'm excited to see how exascale computing breakthroughs could have direct implications for chemists who may never actually run an experiment on Frontier or any of the other DOE supercomputers.
All right. Thank you so much for taking the time to tell us all about this.
Yeah, thank you so much for speaking with me about the story. It's very exciting. Please check out the full version online. And for more updates, as I write them, you can follow me on Twitter at @science_Ari.
Once again, you can find Ari's cover story about exascale computing on C&EN's website or in the September 5th, 2022 print edition of C&EN. We put a link in the show notes along with the episode credits. You can find me on social media as @CraigofWaffles. This has been C&EN Uncovered, a new series from C&EN Stereochemistry. Stereochemistry is the official podcast of Chemical and Engineering News. C&EN is an independent news outlet published by the American Chemical Society. Thanks for listening.